I want to go through the equations that govern the universe on the largest scales under more and more interesting and maybe more and more realistic sets of conditions. And I want to get some solution. It's nice to relate this to observable things, these theoretical equations. So I'm going to take the absolute simplest case possible, which we already solved before. An empty universe, or what I really mean here is a universe where the mass density has been so spread out after a long time that effectively it's an empty universe with a effectively negligible gravity, effectively no deceleration to slow things down. And so we worked out the cosmology equation, basically was the energy equation there, and it came out real simple. Ballistic expansion, linearly expanding universe, all distances proportionally growing larger and larger in a direct constant as a function of time. And so in that case, it's super easy to see what the observers would see. It's very instructive. The Hubble constant, let's see, how is that defined? dr dt, or just r dot is what I had, divided by r. Both of these are functions of time, but in this case, you see, it's a very simple function of time. dr dt is just a constant, which is just c, and rt is ct. That couldn't be simpler. This Hubble function, h of t, is 1 over time, 1 over how old the universe is. Then t is just the number of years, since t equals 0 is the Big Bang. In that case, h naught, that's today, this could be any day, by the way, is exactly equal to 1 over the age of the universe. Or to put it another way, the age of the universe, if it has not decelerated and has not accelerated ever since the beginning, the age of the universe is just going to be the Hubble time. Remember the Hubble time? That's just 1 over h naught. So we could measure it today and extrapolate it boldly all the way back. But, you know, I don't think that really isn't going to be realistic. I don't think we could extrapolate all the way back. But if you could, this is what it would give you. So this is kind of like a limit here if we ignore any decelerations. But you shouldn't ignore decelerations. Here is the formula for a critical zero energy universe. I'm going to write out the whole equation. I have r dot over r, so I've divided both sides by r, and then I've taken the square root of both sides of the energy equation. So we have my usual 8 pi g rho, which is all matter that has mass, including dark matter, that rho is matter dominated, then it must spread out as r to the minus 3. So if r0 and rho 0 refer to the current values of these numbers, then that's the formula for how they evolved back in time. Plug that in, I can get all of the function of r on one side, and I can get all of the function of t on the other side. In other words, I can set up my perfect differentials. I can integrate this differential equation. Those are my favorite kind of differential equations, the one I can integrate. I'm going to put all my constants under the square root sign here. So this rho naught, r naught cubed, those are all constants. Everything under that square root sign is a constant because we got perfect differentials on both sides. So on one side here, I have t. On the other side, I get an r over r naught. I was integrating 1/2, so that integrates up to the 3/2 power. So there's my solution, actually. Whoops. Was there a constant of integration here? Could have been. I set that equal to 0 because I decided we'll have r go to 0. That's the Big Bang at t equals 0. So that was my choice for solution. R as a function of time in a critical density universe. If it starts out critical density universe with 0 energy, perfect balance between the expansion kinetic energy and the gravitational potential energy opposing it, then it stays just barely perfectly balanced forever. That's a very unstable mathematical equilibrium, but let's say that it stays there, constant times t to the 2/3. In a critical density universe, what would the Hubble parameter be? So I need to plug what I've just written into my definition up here. Here's my definition up here. I'm going to plug my solution in there. So I have to take the time derivative 2/3 t to the minus 1/3, I think, if I got that right, divided by, what did we have down here? The constant's going to cancel out, t to the 2/3. It's got to have the units of inverse time. Look how simple this comes out to. 2/3 times 1/t. The Hubble parameter today, 2/3 of the age of the universe, similar to what I had for the empty universe, except the empty universe didn't decelerate. Now, this makes sense. It's just like driving to San Francisco. You can do that at about 80 miles an hour, 320 miles. So if you're just doing that at a constant 80, you arrive there at 80 at the end of the trip. That means you left LA in 4 hours. That's just given by this formula right here. What if you actually have been slowed down by gravity? I don't know, Los Angeles has a lot of gravity. And you actually left Los Angeles going much faster, I don't know, above 100 miles an hour, hot pursuit. So then they zoom in to San Francisco. What would be the age of the trip? It's obviously less than 4 hours because they spent considerable amount of the beginning of the trip going at 100, 120 miles an hour. The oldest it could possibly be is the Hubble time. However, if it's slowed down a lot, it's a critical density universe, then it would be younger. It would only be 2/3 of a Hubble time. If it had really decelerated even more, in other words, if we had a total negative energy universe, which I don't think we do, but if we had a universe that was closed in time and in its future, time and space, then the age universe today would be even less than 2/3 of the Hubble time.
At t equals 0, meaning like when it all began, your Hubble constant would effectively be infinity, right?
Yes, it does seem to be not very well defined right there,
right.
along with everything else, actually, like densities, forces. It looks like it's, I hate to say it, but it looks like this equation has a singularity in it where everything is infinite and cannot be calculated. Physicists really do not like singularities, do they?
Yes.
And in fact, I'll bet you almost for sure there was not actually a singularity there. I don't think singularities really exist. I think when you get a singularity in equations like these equations, the singularity, it comes from a failure of the equation to apply on a very small scale. This is not a quantum mechanical theory. In fact, it's never been really successfully integrated between gravity, on a quantum mechanical scale. In fact, I can pretty much guarantee you these equations are going to be useless earlier than t equals 10 to the minus 42 seconds. But they're probably pretty good after that. I'm going to add something here, which actually is a little bit related to this. If you go back in time very early on, then we happen to know that there are some photons wandering around here today. In fact, it's the cosmic microwave background. They're left over from when the universe was very hot and opaque. Today, it's very dilute, 2.73 degrees above absolute zero. Not that easy even to, unless you have good instrumentation in the microwaves, to even measure this stuff nowadays. But its temperature goes up in direct inverse proportion to how big the universe was, because the wavelength of photons, is proportional to the size scale of the universe. So if the size scale of the universe was much smaller back then, that means all the wavelengths of photons are much smaller, meaning all the energy of the photons were that much larger, meaning the temperature of radiation was that much higher, meaning that the energy density of the photons in the early universe could not be ignored at all. In fact, you can go back to a time when it was more important than the matter, including the dark matter in the universe. So I'm going to try to fix my equation now, because right now my equation could not be valid for the early universe at all, because I've left out radiation. I need to add a term. I need to add the energy density of radiation, which is negligible now, but it was not negligible early on. This is derived very briefly in the chapter 4 at the beginning of Rowan Robinson. This thing here is the energy density of photons. That's an energy per cubic centimeter divided by c squared, that to have the right unit. However, the way that it's usually going to be written in cosmology is a little bit different. Your r dot squared, the kinetic energy term, and that is opposed by the gravitational potential energy of anything that causes curvature of space and time, according to Einstein. Got my rho matter that I was pretty comfortable about, plus 3 times the pressure of the radiation. over c squared. I'm thinking of photons. I'm thinking of anything that's relativistic. This is all. In fact, not only is it all, it turns out it's mostly dark matter. As long as the dark matter now is cold, in other words, it's not moving at close to the speed of light, which the evidence strongly indicate. We've already done one limiting case. Now I'm going to do the other limiting case. So the limiting case that we did is here, we were covering things today where this was ignored. It was just negligible. The redshift has just killed it. But this stuff, and this stuff doesn't have a redshift. But this energy density only falls off as r to the -3. It's falling off. This one has an additional redshift factor. Maybe I'll write this down. It's an important point. This goes like r to the -3. This term goes like r to the -4 because any volume of space has that much less photons, and each photon has less energy individually. If you go back in time, then this is the term that's going to win out because it's a 1 over r to the 4th term. What happens when r gets really small? This totally dominates. And now I'm going to do the solution where this one is negligible. Let's just take that one out, and we'll solve for a radiation-dominated universe. Radiation-dominated and critical universe, where I can ignore kc squared. If you look at these terms, they all go as 1 over r squared. All of the terms on the left here are getting very, very big when the universe was small and close together. Gravity, very strong. Gravitational potential energy, very strong. So, and this is a general statement, when the universe was small, any kind of universe getting started out, this term and this term are dominating. They are so much bigger than the term on the right. I don't really care what the term on the right is. I don't care if k is plus or minus 1 or whatever. It might as well be 0. All early universes act like, evolve like, they're very close to the critical universe. For my r dot, so it's dr dt squared there. On the other side here, in a radiation-dominated critical universe, I got my 8 pi g. Well, rho is p over c squared. It's interesting, the 3 cancels the 3 underneath there. I think that comes from the 3 dimensions of space because you have random motion. Wonder if I could solve that in the same way I've been solving all these equations. I'm going to get the dt, the time function, the simplest perfect differential. I'm going to get that on the right-hand side, take the square root of everything. So I got my dr on the left side. P in general is equal to the pressure at a particular time, and then it goes as inverse 4th power of r. So I can just express it, in terms of some constants for today, which I don't really care about because they're constants. So they're not going to have much effect on the differential equation when I integrate it. So if I plug that in to my equation, my dr, I got to take a square root of the whole thing that's coming along, put a c squared upstairs, 1 over r to the 4th on the bottom, and an r squared, so that leaves me only 2 powers of r now. My constants are all down here, constant of nature there, and then just these constants. I'll just put them down here because I do not care about them. But you all know the trick. Integrate that side, integrate that side. I don't even have to tell you what I'm going to do with the constant of integration. 0 it. And we get our solution. The important thing is it's got an r squared in it because I took the integral of r dr. What you're supposed to notice is r of t, t to the 1/2. The early universe was expanding at only the square root of t rate. And then when radiation got spread out and the redshifts began making it energetically unimportant, the matter took over and altered the expansion rate to something going a bit faster with time, t to the 2/3. And then, of course, at some time in the future, if it became an empty universe, it would go even faster, relatively faster. It would go as eventually r goes as t to the 1, as the universe empties out, completely empty. If I were to use my definition, rho matter is equal to rho naught r naught cubed, that back in here, I could write this equation in a fascinating way. Matter dominates. We've already got our solution. How does time develop? Rho matter is going as r to the -3. So you take the inverse square root of that, and we get that t is going as r to the 3/2. Yeah, that's the solution we've got. You could have almost guessed what the dynamical time scale of the universe has got to be if it's controlled by the gravity of matter. Well, what do you get for a radiation-dominated universe? I'm going to put this back in here. I'm going to put my r squared back in underneath here, which becomes r to the 4th when it's in the square root sign. I'm going to express this as the rho radiation. This thing here, which I defined what it is. So there's going to be a 3 coming out of it, and that's about it. Then I got that 2 became a 4 when I stuck it in down here. And here's the important term. Do you see something so profoundly, beautifully simple? Look at these two formulas. I told you, the time scale of any dynamical system under gravity is always going to be something 1 over the square root of 2 pi g rho with some constant in it. All this stuff about Einstein and the energy of photons seems to go a little bit counterintuitive. Yes, of course, this part, I obviously get it. That's a deceleration. That matter has a gravity, it's pulling everything together. So there is your gravitational potential energy, and it's opposing the expansion. In fact, it might even stop the expansion. Totally get that. But what about this? There's a huge amount of pressure in the universe. I mean, suppose it's dominant. It actually makes the universe slow down. It resists the expansion. This is weird. Look at this term. What happens if the universe expands? This spreads out. This energy density gets smaller. This one also spreads out. This one gets smaller. So the universe lost energy. Gravity did some work against the expansion of the universe. And it doesn't matter whether it's radiation dominated or matter dominated. It's doing some work. It's losing energy. It's slowing down. So it's kind of weird, but the pressure will also oppose the expansion. I'm about to show you the opposite case, which is completely going to blow your mind. Oh, let me just rewrite these equations in a very practically useful form. You can go so far with this one little equation. Okay, r squared minus 8 pi g rho over 3 r squared is equal to minus kc squared. I could divide both sides by r squared. What do I have on the left side? It's my Hubble parameter, h squared. Now this 8 pi g rho over 3, doesn't that look kind of somewhat similar to the formula for rho critical? What we actually have here is rho over rho critical, a dimensionless ratio. Omega value of matter is the ratio of what the actual density of matter really is compared to what the critical density would be, right? So far, I've had such simple cases like this was just 1 or it was 0. Now I'm going to say, well, it might not be 1, it might be 0. In a realistic universe, it might be a 1/10, it might be 3/10. The h squared had to get factored out. Now, when I use that definition, I've totally retransformed this energy equation into extremely useful. What an interesting formula. Remember, I said that you could always scale things because the distance scale can be multiplied by any constant. So you could always scale this thing so that k could be 3 choices only: +1, -1, 0. Well, if it's 0, we got a very simple equation here. If k is 0, then obviously omega is equal to 1, and we already have the solution that we started with at the beginning of the class here. A perfectly critical density universe starts out as a critical density universe, continues as a critical density universe, and always, if it was tuned exactly perfectly at the beginning, remains a critical density universe. H was r dot over r. So if I multiply both sides by r squared, then I'm going to get a formula for r dot. Let's suppose that it's an open universe, but not an empty universe. So let's suppose, for example, that omega is not 0. That was a trivial case that we considered first. And it's not 1. There's another trivial case that we considered. Let's suppose that it, like I said, it might be about a third. R dot, according to these equations, is going to eventually tend to the current Hubble constant that you measure times 1 minus the current value of omega. R as a function of time. Here, I showed you the simple ones already, but the more realistic one is R starts out going as t to the 1/2, then it's t to the 2/3. At some point in the future, it just goes ballistic. It goes straight line. So that's actually pretty realistic. Each of these transitions, from this zone here to this zone here to the ballistic free expansion, just linear expansion thing, corresponds to switching over from one term in the equation, the energy equation being dominant, to another term in the energy equation being dominant. At the beginning, we had radiation pressure being the dominant thing. Then we had the gravity of matter being dominant. And finally, that became negligible. And it was just this kc squared term was the only one left. And that was very easy to solve. So that's your general solution there for open universes, except that I've left out one thing. Was happy to leave this thing out. In fact, I did leave this thing out when I was teaching the course, as a young assistant professor, because nobody thought that we needed to have anything else in there. So I got my kinetic energy term here that can be expressed as a Hubble constant. I got my gravitational potential energy term here. I can include rho of baryonic matter. I can include, like you said, rho of dark matter, and I can include rho of the photons. I got all that in here. Now we know how to deal with it. This term has something to do with the shape of the whole universe, the geometry of the universe. It's kind of weird to say, but according to relativity, and this is one of the odd things that I don't know if Einstein instantly realizes, but other people around him did and started pointing this out. The shape, the geometry of space-time itself has energy. That's why it has to be included in the energy equation. And it can be either positive or negative or zero. Only zero if you have a flat geometry, Euclidean geometry. But in general, it's either positive energy or negative energy. Einstein realized I could add something else in here as long as it's a constant. Because he had a very strong reason for wanting to add another term. This term is so outrageous. It's so revolutionary. It's so bizarre. I'm going to put it in red, but I'm going to add it here. You can't stop me from putting it in here. What the heck did you just do? His beautiful equation. We'll call it the Einstein cosmological constant here. Let me give you one other definition. Remember this omega term? Omega keeps track of how important something is compared to a critical value. So I'm going to define omega lambda here. This is a little bit of a weird definition. So tell me how important that one is. The same way I define omega matter. Omega matter was rho over rho critical. Well, this thing has an energy density too, lambda. I'm going to define it to be the units are correct. Then it has the right units here. It's dimensionless. If I give you that definition, so I got 1 minus omega m minus omega lambda. Let me look at the top equation though, okay, and see what's so attractive and scary about this term. This thing is definitely supposed to be positive. And this is the weird thing. It's just a constant, an energy density of the vacuum. And of course, when Einstein did these equations, there was no evidence for such a thing to exist at all. I wonder why he put it in. He wanted to have a term that would oppose the gravitational deceleration of the universe. He was concerned, just like Isaac Newton, that the gravity would collapse the universe, and he wanted, out of his natural prejudice, intuitively, he wanted to have a static universe. The expansion of the universe is doing work. In other words, the energy density of matter, and this is also true of photons, goes down as the universe expands. It takes away, it robs the expansion of its kinetic energy because the expansion has to do work to spread out the baryons, the dark matter, the photons, the neutrons, and everything. It's doing work to do that. This lambda term is the opposite, the constant amount of energy. I mean, you could measure it in ergs per cubic meter of space. That is the weirdest thing I've ever heard of, because that means what happens when the universe expands. When the universe expands, there's more cubic meters physically than there was before. And each one of them has lambda. It's a constant. The expansion caused more energy to be present than was present before. It's the opposite of the expansion doing work. The vacuum energy is doing work on the universe. The universe always wants to have more energy. It can get more energy for free just by expanding. The vacuum energy here wants to make the universe expand. That's the exact opposite of gravity or anything else we can think of with slowing down the universe. You have come up with something, which God knows what it is, that will cause the universe to naturally want to expand, to make more volume, to make more energy out of. Suppose that this term was a dominant term. This is not what Einstein wanted, but I just want to go with that. You see, this term does not go down as the universe expands. This term, the curvature term of the universe, gets smaller and smaller as the universe gets bigger. This term here, the gravitational potential energy universe, that gets smaller and smaller as the universe gets bigger. So as the universe gets bigger, this term gradually, as we saw, becomes unimportant. And even this term gradually becomes unimportant. And as we worked out before on my equations, those are the only two terms I cared about. I'm going to take the square root of both sides. Forget about all those terms that vary as a function of r. dr dt over r, square root of a positive number, that's okay, square root of lambda over 3. Oh, that one's pretty easy to solve. The time derivative of a function is just proportional to a constant times the function. Everybody can solve that. Exponential e to the, oh, and it's all positive here. Basically an exponential expansion. A runaway universe. If lambda ever even starts out as being anything, if you wait long enough, it's going to have a chance to eventually take over everything and drive an exponentially expanding universe. I know this seems quite odd, but what I'm saying is it still is a valid solution that satisfies all of the equations of general relativity. This is a fully consistent solution of the field equations of Einstein's relativity. In the simplifying case of an isotropic homogeneous universe, which is the only case I'm interested in. Even Einstein early on realized that you could set it equal to 0. Everybody's been setting it equal to 0. Just in the last 15 years, people said the observations are telling us it's not 0. The reason Einstein considered it was he constructed some fascinating mathematical curiosities explained in killer detail in Rowan Robinson's chapter. He's got Einstein's actual solutions with a critically tuned lambda. So where r of t could actually be constant for a long time, you have to balance the value of lambda and the density of matter. You can kind of see it in the equation right here. If I got this thing to be big enough, he was actually able to get a series of equations, which you can see them plotted in Rowan Robinson's chapter, which would make it 0, r dot equals 0. I'm not spending any time on those because they have no relevance to anything in the universe, except Einstein thought they did because he thought we lived in a static universe. This is static for a long time, but it's not really stable. At some point in the infinitely far future, eventually go over to an exponential expansion. We call it a fudge factor that he added here because he was so desperately anxious to come up with a solution to the universe that would be static for a long time. Trillions of years here, we're living in that. Just his enormous cleverness. About 18 months later, he found out about the discoveries at Mount Wilson, and he said, oh, mein Gott, it's an expanding universe. I never really should have put this in here at all. I wasted all that paper on these static solutions, which actually don't apply to our universe. It is my greatest blunder of my life. So let me draw the first real evolution of the universe that I've shown you. I've shown you all these artificial special cases. Now I'm going to make a big one here. For the first time, I'm actually going to get real. There's time. There's r of t. Start out with t to the 1/2 very early on. Then it goes to t to the 2/3. At some point, it might actually sort of go straight for a while, but then lambda takes over, and it starts going like that, exponentially expanding. How far does that exponential expansion go? That's an interesting question. What is our situation of modern observational cosmologists? We're trying to figure out the future of the universe, but we also need to measure what the expansion rate in the past was. You can see that this expansion rate has not been a constant. Sometimes it's been slowing down, decelerating, and sometimes it may have been accelerating. We find ourselves at T naught here trying to figure out what the heck is going on. And our key observation that we did the entire Hubble Space Telescope key project on, we figured out exactly what the slope was at one point in time. We have really measured that. Well, that's the expansion rate now, but what was the expansion rate earlier in time? But if you go back in the past, there were many universes that could also be consistent with the current value of Hubble constant. For example, we could have been just a critical density universe. There it is. In which case the expansion started what? How far ago? 2/3 of a Hubble time ago. That's one possibility. Another possibility that was interesting is we could have had, this is weird, an empty universe with negligible gravity all the way to the beginning. I mean, I don't think people are taking that one too seriously now, but there's a straight line all the way back. In which case, the age of the universe would be one Hubble time. But actually, the reality gets even more bizarre. It looks like real universe is shown in black here. It was the acceleration recently. By recently, I mean in the last several billion years. The universe was actually expanding at a slower rate. It was expanding, but at a slower rate then than it was now. But then, of course, earlier on, it decelerated. So it decelerated, and now it's accelerating. Sorry if I didn't draw that real good. The actual age of the universe, it doesn't have to be 2/3 H naught. It doesn't have to be one Hubble time. It could be anything. But because both of these effects, let's say by accident, to be fairly comparable, the actual age of the real universe happens to be approximately one. What is it? I don't know, 0.98 Hubble time, age of the universe. The earlier work in the 80s had lambda being 0. And people were seriously considering that dark matter was enough to make a critical universe. But there was a problem that's a fairly short-lived universe. The problem here is that 1 over the Hubble constant, it's what, about 13.7 billion years. And this was an outstanding problem that was known to everybody. Ages of the globular star clusters. What are the longest lived stars in a globular star cluster? They all formed together. They were all born at the same time, a long time ago. What are the longest lived stars that are still alive, that are still on the main sequence? For example, can you find stars like the sun, one solar mass, that are currently, up at the end of the main sequence of a globular star cluster? No, they've all died. They all went through their red giant phases, and now they're white dwarfs. The most massive star that you can see at the turnoff, that's the end of the line of the main sequence in the color magnitude diagram of current globular clusters, is known to be about 0.8 times the mass of the sun. Well, but say 0.85. Those stars have a longer main sequence life than the sun. What is the main sequence lifetime of the sun? 10 billion years. It depends a little bit on how convection takes place in the sun to give you a little bit more hydrogen fuel. But basically 10 billion years, I'm going to go with that. So there are globular cluster stars on the main sequence which are still not dead, which have 11.5 or 12 billion year lifetimes, and they're just dying now. So the globular cluster lifetimes, through a great deal of work and interpreting their main sequences with stellar evolution models, are 12 billion years old. So the age of the universe is known for a pretty number of decades here. It has to be larger than 12 gigayears. So one of the reasons that the Hubble Space Telescope Key Project got all of its time is they really wanted to say something about the age of the universe. If they had come up with, and many people advocated, a very small value for the Hubble constant, like 50, that would have given you a Hubble time of 20 billion years. In that case, a critical density universe, which is what people were thinking about, would have been around for how long? 2/3 of 20 billion years, 14 billion years. No problem for accommodating globular star clusters, no conflict. In fact, they use this. We say that it's 50. There's some people in this room that say that's 80. They must have made a mistake, because the globular clusters then would be older than the universe. The globular clusters would be have been around for longer than the Big Bang, which is impossible. You can't be older than your mother. Adding this lambda term, which is actually now called dark energy term, changed the whole argument about the age of the universe, made everything come out okay, and resolved it. Yes, the globular clusters are 12 billion years old, but because the universe it did decelerate in the past, yes, but because it's now been accelerating for billions of years, this gives us an older universe, consistent with the globular clusters forming sometime after the Big Bang.
The black line that you said, or the black curve that you said was representative of our universe.
Yep.
Is that the same as your previous drawing where you had the T to the 1/2 radiation dominated?
Very good. It's the same, except that I have now changed the future here. I put in this part. Oh, there was never actually a period where it really was T to the 1.
Okay.
Maybe it was T to the 0.8 or 0.8. I hate to tell you, but the equation for this black thing, it's not analytic. It has to be solved numerically. If this term really is a constant, then yes, it'll go gradually over into an exponential expansion, which seems to run away. And of course, maybe we don't understand what this is. Maybe this actually might change a little bit in the future, or change at very large R or something. But if it really literally, nobody knows. I mean, we didn't even know that there was a term here at all. But if the term really is a constant, then that expansion just keeps going exponentially faster and faster. In principle, this is a big extrapolation, could be wrong. The expansion will be so exponential that everything will move out of our horizon. We'll be no longer able to see any other galaxies at all, just our local group. And then the expansion will be going so fast that it will eventually start tearing apart objects that are gravitationally bound, such as the local group of galaxies. That's what a runaway expansion is, because space will be expanding faster, stronger than the gravitational attraction, even of these very overdense regions. Even the overdense region of the Milky Way will start tearing apart, if this is correct. Even systems of planets will be torn apart eventually. Even stars won't have enough gravity to eventually hold themselves up against just the expansion of space. Even planets will be torn apart. Even macroscopic objects, the space will overcome everything, expand it. In fact, in principle, at some point, if you carry this to its absurd conclusion, even atoms, which are finite in size, would be torn apart by the expansion of space. Everything would be torn apart. Everything would be destroyed. It's called the Big Rip. We don't know if that's going to happen, but I mean, if you literally take the equation, Big Rip, that's almost as scary as a big crunch. The existence and the nature and the cause of this dark energy, I consider to be not just one of the most outstanding problems of astronomy. It is one of the most outstanding unanswered mysteries of science, all of science.